All right, guys, so we're going to get this started. Go ahead and pull out your notes. You should find them in e-backpack. I know that this is chapter 17. The ones you have say chapter 14. Apologize, didn't have time to change this PDF. All right, so today we're going to be talking about groundwater. And as the name would imply, it would be water found underground in cracks and spaces in soil, sand, and rock. So yesterday we were doing a lab where you guys saw that soil is going to be made up of sand, silt, clay. But then we also know from our previous discussion of soils that you have that mixture of air and water and then organic material. So depending on the different composition of the soil, you will have different levels of water that are able to not only make it into the soil, but also then collect. So different soils will have different water levels, but also different rock types will affect what type of water level you have in there. So we're going to get into a little bit of that as we do the chapter. But overall, I want you guys looking at this chapter from the perspective of the water that you drink, the water that you bathe in, the water that you wash your car with, water the lawn, all of that on Long Island is coming out of the ground in the form of, or from what we call the Long Island Aquifer. So that's the big storage area underneath the ground where all of our water's coming from. I just want to set that framework so you guys are understanding this is something that's relevant to you guys. And this hopefully is something that over time you'll become a little more concerned about, because your drinking water coming from the ground, if that were to, get contaminated, that would be a little bit of an issue. All right, I've done enough talking. Let's get through some notes. So right off the top, you need to fill in the definition for groundwater. Again, water found underground in the cracks and spaces in soil, sand, and rock. Now, this is the storage area, or if you recall in the previous chapters, we use the word reservoir. So this is going to be the largest reservoir of usable liquid freshwater. Remember that the largest reservoir of freshwater is glaciers, which we'll get into in the next chapter. But groundwater makes up a considerable amount of Earth's hydrosphere at 0.6%, and that's going to be pretty substantial when you look at the amount of fresh water that's actually available. Okay, so how does this water get into the ground? Well, we have infiltration in the hydrologic cycle when water hits the ground and starts to seep down into the soil. If you look at this diagram over here, this shows you the different levels of what's going on inside the ground. So up where we have the happy little trees, right over here, little Bob Ross action, you have the terrain, and then when the precipitation comes down, it's going to initially infiltrate through this area that we call the unsaturated zone, or the other term we like to use, and you'll start seeing in the coming days, is the zone of aeration. Now, that doesn't mean there's no water there. It just doesn't. It just means that it's not filled, right? It's kind of like having a towel in the bathroom, right? You're going to get into a shower. Well, if you pick up that towel and it's super dry, we'd say it's unsaturated. If maybe somebody dried their hands off, right, and you grabbed it, well, there might be a little bit of water there, but it's not saturated. Even after you have dried off, it's still not saturated. We'd still say that it's unsaturated. However, if you drop that towel like in the bathtub, or you drop it in the pool, and it soaks up all the water to the point that water's dripping out of it, that would be saturated. So I want you guys thinking saturated, there's no more room to hold water. everything's filled, but the unsaturated or zone of aeration means that you haven't hit that saturation level. So it could be dry, it could have a little bit of water, but it's not going to have that level of water that you would think of if you want to wring something out. Now, underneath that, we have the zone of saturation, or the saturated zone, and that's going to fill all the way up till you hit this neat little point called the water table, right over in here. So the water table is the top of the zone of saturation. So the water infiltrates down or permeates down into the soil. Permeate is a word that we use for the ability of water to pass through a material. So it permeates down, and then it's going to start to collect when it hits that lowest point in the soil that it can permeate to, and then starts to build back up. So it fills up, fills up. The top of the full zone is what we refer to as the water table. I guess it would be a good time to give you a hint. That would be a good diagram. This one right there. Yep, might be a good diagram, for a quiz or something like that later in the week. All right. Again, I've said too much. So, how does water actually move through the soil? Well, we got our little friends over here, little water molecules that show that you have cohesion and adhesion. Now, cohesion, as you can see, two little water droplets sticking to each other. That's because they want to cooperate, right? They want to work together. So cohesion is the idea that two things stick together, two like things stick together. If you're on a sports team, it's really important that you have cohesion among the players, right? If you don't have cohesion, you're not all working toward the same goal. Adhesion is the ability of one material to stick to another. In this case, water's ability to stick to another material, maybe like this leaf-looking thing, or to the windshield of your car, or to the fibers in a towel, right? That's adhesion, to adhere, kind of like tape, right? If you have duct tape or scotch tape, right, it sticks to another material. We call that an adhesive that allows that sticking to take place. So water molecules kind of cool. They're able to stick to each other. They're able to stick to other materials. And in our case, talking about groundwater, they have the ability to stick to other grains. So whether it's sand, silt, clay, water is able to stick to them. So when water sticks to itself, it will both pull down, but also has the ability to pull up, as you're going to see in what we refer to as capillary action. So capillary action, I'm just going to try and center this nicely for you guys. Right? Capillary action is the movement of water within the spaces of a porous material due to the forces of adhesion, cohesion, and surface tension. If you recall in the previous chapter on freshwater, we talked about water is a polar molecule, so it has a positive side, it has a negative side, and therefore it makes this attraction. That's what allows for cohesion to happen. But it also allows for this concept of surface tension. So surface tension molecules are sticking to other molecules, but temporarily creating this high surface tension. So that's oftentimes you can like smack water, or maybe your friend belly flops into the pool and you can see like they come out, their chest is all red because of that high surface tension. It's a temporary thing. It's also why divers, if you ever watch diving, I don't know why you would, but apparently some people do, they have a little spray nozzle that sprinkles out over the water. And what it does is it breaks up that surface tension so that when the diver comes down, they're not hitting the water like a solid surface. I'll explain that more tomorrow if you guys are confused. I digress. So these are capillary action tubes, and what the point is behind these, and I have a set, I'll show them to you tomorrow, is that as the pore space gets smaller, so when we go from a half inch on the left over here, all the way down to like a 1/16 of an inch diameter tube, water has a greater ability to rise higher and higher. Now, let's think about this in a biological sense, right? You have roots at the bottom of a plant or a tree, right? And those roots are really, really small, really gnarly, hairy little roots, right? But they draw some water in, and by adhesion, cohesion, and capillary action, they draw the water up. And they give a greater and greater supply as it moves into the larger parts of the plant so that you can bring the water all the way up. In the same way, soils have that ability. And in particular, sands are really good at drawing water up because they have just the right pore space, large enough that water is able to make it through, but small enough that you're not losing that adhesion and cohesion concept. So speaking of sand, we have this thing called an aquifer, right? Again, it's a reservoir, but an aquifer is basically a rock or soil through which groundwater moves easily, i.e. sand or gravel. This is going to be an area we're going to store water. The opposite of that, we're going to use a fun word called aquitard. And aquitard is actually an impermeable layer. So when you see aquitard, it means that water's not going to be able to pass through it. Hopefully some of you all just scribbled that in much better than I did. That wasn't the eraser. Oops. All right. A little bit better. Now, let's get into this a little bit further. Your climate, the gradient, right, the steepness of slope, the rock type that you're dealing with, the amount of vegetation. These things sound familiar. Oh, that's right. These would all be factors that determine whether or not you're going to have runoff or infiltration. Well, these are also going to be factors that are going to affect the availability of water to infiltrate into the ground. I'm hoping that kind of makes sense. Again, I'll review some of this tomorrow. Now, we talk about the idea of a water budget in the sense of when we have a lot of infiltration and not a lot of the word usage, you're going to start to get a surplus. You're going to get some extra water. In the same way that if you put more money in your bank account than you take out, well, then you're going to have a surplus, right? You're going to develop a larger and larger savings. The inverse of that, if we use more than we put in, well, then we're going to create a deficit, or you're going to go into debt. So deficit, debt, surplus, savings. There are going to be certain times, of course, that we're going to be more likely to have a surplus. Like right now, we're getting lots of precipitation lately, some rain. We go into the April showers. Our groundwater levels tend to rise in this spring portion. During the summer, when we go through some droughts, we're still using the water the way that we normally do, and oftentimes people are using excess water, because we all need to have green lawns, right? People have to wash their cars 5 times a week, and therefore you're going to cause a deficit because there's a lot more usage than is infiltration. And the cool word for infiltration here that we're going to use is called recharge. I know, it sounds cool, right? Recharge. So we need that recharge in order to build up and to really maintain our groundwater. But in the big picture, right, sometimes we put groundwater in that actually remains there for thousands or even millions of years. And for that, we refer to it as fossil water. Now, there is some, sorry about this, it's getting all kooky. There's fossil water actually underneath the Midwest in what's referred to as the Ogallala Aquifer. And you guys are going to read about that. But the Ogallala Aquifer has existed for thousands, hundreds of thousands of years. Water in the crazy, I mean, the numbers are staggering when we get into it. The point is that we are so good at using that water that the aquifer is drastically in deficit mode. And there are no indicators that we're going to turn that around. There are no indicators that are going to, or that are showing that, hey, we're going to use a little less water and allow for some more recharge. In that case, you can actually run an aquifer dry. You can deplete an aquifer to the point that in our region, right, being along the coastline, you can actually allow salt water to actually seep into your aquifer, which now contaminates it. So there are a lot of different issues. So groundwater is actually a pretty big deal because this might be news to some of y'all, but you need water to live, right? And we primarily get our water from the ground. So some of y'all right now are like, oh, he's talking so much. It's a Tuesday. I wasn't ready for this. But these are actually some pretty serious issues and ones that I'm going to hope that you guys start to pay a little more attention to. All right, so the next point on here, talking about aquifers, is this actual concept of porosity and permeability. So porosity, like look at your hand, your skin right now. You got all these little pores, right? They're these little open spaces on your skin, right? And that's where like the sweat comes out. Well, in rocks, we want to know, or in the ground, we want to know how much pore space or how much open space is in a rock, because that's going to help us to understand how water will be able to pass through it. So the definition that I'll probably run with would be the percentage of the total volume of rock or sediment that consists of pore space. Now, this is the crazy part. I'm glad I'm pausing on purpose. Clay, and you guys just saw like a clay texture, and sand, and gravel have a pretty similar porosity. Clay actually has a really high porosity when we really want to get into the details. But it's the interconnection between the pores that will give us what we call permeability. So the ability for water to pass through the grains is not directly related to the porosity, right? You need some space in there in order to be able to get water to pass through, but it's important that you guys understand that a high porosity does not necessarily mean that you're going to have a high permeability. So let's go find permeability. So I'm going to apologize now. They updated this app, and I'm having a couple issues with it. Okay, so permeability, a material's ability to transmit water, right? Yes, it's important to have pore spaces. Yes, it's important that pore spaces are connected. However, high porosity does not mean high permeability, and that's in your notes here. It's going to be a pretty big deal, so make sure you all take a little time to understand that one. Okay, so what are some factors that are going to affect your porosity, right? What's going to affect the amount of pore spaces? Well, the shape of the grains are going to be really important. If they're all really well-rounded, well, you're going to develop a lot of pore space in between, which is what you're seeing in this diagram over here, right? You got this diagram. You can see all the blue on the right where it says spherical particles. That means they're round. On the right, the angular particles, the angles, the little sharp points kind of find their way into the other corners and crevices of other rocks, and you see a lot less blue shining through. So the one on the right, high porosity, the one on, or as you move to the left, the lower porosity. And the same idea, if we have really well sorted, meaning all the same size grain, you're going to have, again, a high porosity. Because if it's all the same size grains, it's like taking a whole handful of marbles, right? They're all the same size. You're going to have a certain amount of pore space there. But if I start mixing it up, and I have pebbles and cobbles and sands, I can actually start to fill in those pore spaces, kind of like a cement, but granularly. That's going to take up that open pore space, and therefore you're going to have a low porosity. So that's what we're trying to indicate over here. All right. Now, let's get back to the big picture. And here you go. So this permeability, this porosity, gonna start to become a bigger issue if we want to understand why water would seep into the ground or why water would not seep into the ground. So this brings up one of my favorite things to talk about, which would actually be the idea of window wells. Now, if any of y'all have a basement, I don't, because I live over in Levittown, right? We just have a slab. But people with basements, if they don't dig a little well like you see in this picture around their window, what happens is when the rain really comes down, I'm talking those heavy downpours, and infiltration just isn't enough, right? The water's going to start to look for somewhere to go. And if the easiest place to go is in your window, well, then you got to flood in the basement. And that's a little bit of an issue, right? Because nobody really wants a foot of water in their basement. I mean, it might be nice to have a swimming pool, but that's more like organized. I can tell you this story, though. When I was your age, and yes, that's a very long time ago, my uncle had a house built out in Jamesport. And the builder so nicely bulldozed all the topsoil and then graded what we call fill in over, and basically just garbage soil, really rich in clay. And so he moves into the house, he's all excited. We have the first Christmas there, and then right around March he gets really heavy rains, which is kind of typical. Only because the permeability of the soil in the backyard was so bad, because it had so much clay, really high porosity but really low permeability, the water basically just collected, and he literally had a pond in his backyard, or lake. I guess lake because it wasn't spring fed. Only the only place for that water to go was into his basement. And he ended up with about 6 feet of water in his basement. And then it got better because he tried pumping the water out. Somebody goes, oh, get one of those, pumps, and you just pump the water out and makes it better. Only as he pumped it out into like the front yard, it seeped into the ground. The groundwater level was already pretty high, and it just came back down through his foundation. So quite the problem. One of these reasons why I try to spend time talking about permeability, porosity, and, soil composition. Because someday you guys, might be fortunate enough to have a house built. You might want to pay attention to what your soil looks like and what the groundwater situation is around where you're planning to live. Or, you can spend $25,000 and have a French drain put in your basement and then still have mild water problems from time to time. Anyway, I've digressed. I apologize. Let's get back to permeability, porosity. So this window well over here is an avenue for water to get down into the ground quickly. And if you look in there, there's a lot of gravel because gravel has a really high permeability. It allows water to get down into the ground very quickly. So anytime you see somebody putting a well in, somebody wants drainage, they want big chunks of rock that are going to allow water to pass through quickly. They're not going to go and make a clay layer, right? Because clay is classically impermeable. If I wanted to go make a pond in the backyard, I'd go get some clay and like line the whole thing with clay because I know the water's going to sit there. It's going to take forever for water to make it through the clay. And just think about, pots and stuff like that. Go back to like Mesopotamia, right? What they used. They used clay and then they baked it. Now, that makes what we call an impermeable layer. And there are a lot of impermeable materials. Not sure what happened there. Apologize. One being clay, obviously. Another being asphalt, plastics, glass. Even for some of you guys, like your ski jackets, the Gore-Tex, like that's supposed to be an impermeable layer. The idea is that you have a material that water cannot pass through. That's all it means. And the term we used before was an aquitard. Aquitard is an impermeable layer that's going to form in the ground, and it's going to either trap water underneath, where we'll end up with what we call an artesian aquifer. Basically, we have an aquifer where the water's coming down, getting trapped and pressurized, or that aquitard can act as like a base layer, and now the water just starts to pool on top of that. Now you're filling up that zone of saturation, and somewhere above there you'll have your water table. All right, I know I've thrown a lot at you guys today. I want to encourage you when you do your reading and outlining to reference back to these different things that I'm trying to make mention of. Over here, another version of a groundwater diagram where you have your bedrock, you have your saturated zone, your water table, above that your zone of aeration or unsaturated zone. These are all going to be super important as we move through this chapter. If you guys can piece that together in your outlines, really focus in on what these different layers have going on in them, it's just going to set you up in the right direction when we pick up on Wednesday. To the teacher that's covering, I do appreciate you taking the time today. And you guys have a good afternoon. Go ahead and start your outlines. And thanks for listening.